Right, okay, so this is going to be the last lesson on pneumatics then, and this is the lesson on the mathematics of pneumatics. So, I'm going to take you through the principal equation that we use, which is about pressure, force and area, but then we're going to have to talk about circles as well, because cylinders are based on circles. And whenever we're talking about area, we're talking about the area of a circle, generally. So on outstroke, we're talking about the area of a circle. On instroke, we're not talking about the area of a circle. We're talking about the area of like a donut shape, which is based on circles itself. So we need to know about how to work out the area of a circle and then how those kind of quantities interact with each other. So let's start off with the fundamental kind of quantities that we care about when we're talking about the maths of pneumatics. We'll be talking about pressure, we'll be talking about force, and we'll be talking about area. The kind of shorthand, we'll use P. For pressure, the units are newtons per millimetre squared. For force, we'll use F, and the units are newtons. And then for area, we'll use A, and the units are millimetres squared. What is pressure? Pressure is that idea about how much force has been applied per unit area. Right, so like I'm sitting here right now, and I've got miles and miles of atmospheric gases above and around me, all weighing down on me through gravity, and they're applying a pressure, they're applying force across my entire area that's exposed to that pressure. I am a human being, I have evolved to be strong enough to move and breathe under this pressure. It would be different if I was at the bottom of the ocean, because the pressure would be much greater because of the mass of the water. It would be different if I was in space, because the pressure would be much less and I couldn't survive there. But right here in this scenario, there is pressure weighing on me. What pneumatic systems do is they soak in air into a vessel and increase that pressure, just like us forcing air into a balloon. It's kind of different because the volume of the balloon increases and the pressure has actually been applied, or pressure has been created by the elastic nature of the skin. You've got a lot more expansion in that skin than actually happens in the tank of the compressor. The tank of the compressor, air soaks into it and fills up. The tank doesn't change size, the tank stays the same size, and the air pressure increases as you force more into that volume. The pressures that we use, the compressors in our department, stop compressing at 0.3 newtons per millimetre squared. Atmospheric pressure that I'm sitting out is about 0.1 newtons per millimetre squared. So the pressure in our systems is 3 times atmospheric pressure. So if you open a connection to the hose, air will rush out because the air inside the tank is at a higher pressure than the air outside the tank. There's a pressure differential between the two. There's a difference in the two pressures, and the pressures will attempt to equalise. If you leave the hose open, all that air that's pushed into that tank at 0.3 newtons per millimetre squared will rush out, and you'll be left with atmospheric pressure inside the tank and atmospheric pressure outside the tank. Okay, and it's that movement, it's that pressure differential that creates movement of cylinders and things. Force is just a measure of strength, right? So force describes this cylinder here, when it moves, how strong does it move? We could put a number on that. We could put a number on that in newtons. How much force will it apply to something? Yeah. And then area is the area of a circle, right? So we are principally concerned with area equals pi r squared, because these cylinders are circular in section. Sometimes it won't just be A, we'll put little subscripts in there depending on what area we're talking about, because we've got the area of the cylinder itself, but we've also got this circular cylinder rod that goes in there, and that cylinder rod meets on a circle inside there as well, so we'll care about the area of that footprint too. So we'll have to put like area of C, AC, and A cylinder rod, ACR, and then another one called effective area, so EFF. So we'll put some subscripts under area depending on what we're talking about as we work our way through. And it would be nice something, as an extension. This tends to be a little bit beyond what National 5 SQA ask for, but to be able to work out if you've got an area, what would the diameter be? So this is if you've got a diameter or a radius, then you can work out what the area must be. But it's nice to be able to go the other way and go, right, so the radius equals the square root of a over pi. That's just rearranging that equation. So yeah, those two, although that one on the right hand side is kind of an extension. So let's look at this in its most basic form. In its most basic form, we've got the equation that we use is pressure equals, I think this is Boyle's law, I'm not sure, equals force over area, or P equals F over A. It's in the data book. You should be able to rearrange this into the other two forms. So right now we've got P equals, that's if we don't know pressure but we know force and area. But what if you know, what if you're looking for force? So force equals, and if you rearrange that equation, force must equal pressure times area. And we could then rearrange this for area. Area equals, kind of the hardest one to rearrange, you put the A up there and then put the P down there. F over P. So that's the three forms of that equation. This is I think this is the one that they give you in the data book. You should be able to rearrange it into those other two. And in an SQE paper, they'll give you two and ask you to work out the third one. So they'll give you a pressure and area, ask you to work out a force. So as an example, if P equals 0.30 newtons per millimetre squared and force is 125 newtons, what must the area be? So we're using this form of the equation. Area equals force over pressure, 125 divided by 0.30. Divided by 0.30. 125 divided by 0.30. 416.667. 416.667 millimetre squared. Round it to the correct number of significant figures. That's got two significant figures, trailing 0 after a decimal point. That's got 3, so it's two significant figures we're rounding it to. So that's 420 millimetre squared. So that's the type of exercise you would do. You've got two of them and you have to work out the third one. Fantastic. Sometimes you might have to work out the area before you can do that. Sometimes they might give you a diameter of something or a radius of the cylinder and ask you to then work that out. So what would that look like? So they might say if pressure equals 0.30 newtons per millimetre squared and force equals 240 newtons, what must, oh no, wait a minute, I'm asking this a silly way. Yeah, right, so yoink. And area of the cylinder, no, that's not the question I would ask. And the cylinder has a diameter of 25 millimeters. What will the force be? On outstroke, and when we really cute in there and put outstroke in there for a very particular reason that we'll come back to later. So in this one we've got pressure, and we know that we're looking for force. So that must mean that we'll be able to get an area somewhere. We're going to calculate this area. It gives us a diameter of the cylinder in there, it tells us 25, so I can use this equation. Diameter is twice the radius. Hopefully you remember your kind of theory of circles, yeah? Here's a circle, there's a radius, and there's a diameter. So if you know the diameter, you know the radius, because the radius is just half of the diameter. So that means that our area in this question, we're going to have to calculate the area first. Multiplied by radius squared, so that's half of the diameter, 12.5 squared equals, and we put that in the calculator. So 12.5 times 12.5 multiplied by pi, and it's 491. 491 millimetres squared. I'm not going to round that because it's not a final answer. That's us got an area. We can now stick that into our force equals the format. So the equation in a data book is pressure equals force over area. We rearrange that for force. That gives us pressure times area. And then we can stick our numbers in. Equals. So 0.3 multiplied by 491. 147.3 newtons. And then we look at our data points. That's 2 significant figures, and that's 2 significant figures. So we should be rounding this to 2 significant figures. Yeah. So in this question here, we've had to work out an area first. Right, and I put outstroke in there, right, because sometimes when you have to work out the area, it might be a little more difficult. If you're using a single acting cylinder, right, remember a single acting cylinder is that one. We only use here to outstroke it. So if it's a single acting cylinder system, it's always outstroke. We're always, if we're asked to do calculations, it'll always be outstroke calculations that we're doing. And that's pretty much what you would be asked to do. That's like the hardest thing you would be asked to do, work out the area. If it's a double acting cylinder, then it's not necessarily always in-stroke, it's not always outstroke. It could be in-stroke or outstroke, or I mean they might even ask a question when they ask you to do one and then the other. You might have to do air going in here, which is outstroke, but you might also have to do air going in here, which is in-stroke. And there's a difference, right? And this is the problem. Right back at the start of this, I gave that kind of thought experiment, and I gave you the answer about what would happen if you took a double acting cylinder and connected both ports to main air. The expectation is that people would guess that it would just stay static because the pressure on both sides is the same. But if you build it in real life, it very slowly outstrokes. It's almost like it's developing more force on outstroke than it does on instroke, which is strange because it's the same cylinder and it's the same air pressure. What's the difference? The difference is the area. Okay, so if you've got this cylinder here, right, if you put air in to outstroke it, what does that air see? It sees an open face. You can't see inside it, but you know, if I were to draw this guy in like 3 dimensions, you know, do a wee pictorial of the actual part of the cylinder that moves. Yeah, looks like that. So on outstroke, and this one's got like that wee ball actuator on there, so a wee ball on there. So this is the bit that moves in and out, the actual cylinder itself. So right, so what we've got is on outstroke, this is the face that the air pressure sees, and that's a circle. Fantastic, that's what we're doing up here. That's why I wrote outstroke in there. That's why that's what you would do for single acting cylinders, because it always sees that. If you turn it round the other way, when you've got the ball actuator on there, and then you've got the cylinder rod coming back, it meets the face there. That is not a circle. It's not a circle. That face there. I'm going to make it red. It's not a circle. That face is, if you look at it straight on, it's that shape. Based on 2 circles, I know it's badly drawn, based on 2 circles, like a donut. It's a donut shape. I think it might be called a toroid, I'm not sure. I don't know if that's a 3-dimensional thing or a 2-dimensional thing. Yeah, it's a donut. So it's the area, that red shaded area there, is the result of the area of the big circle minus the area of the wee circle. You can find the area of that one and subtract it from the area of the full one. That will leave you with that red area there. And the area of that small circle is based on the diameter of that cylinder rod. And this is on instroke. So the area on instroke is actually smaller than the area on outstroke because of the piston rod, right? And that's why it's different, and that's why you're watching out for this word in the question. Am I talking about instroke or outstroke here? Is this a double acting cylinder or a single acting cylinder? If it's a single acting cylinder, things are easy. If it's a double acting cylinder on outstroke, things are easy. If it's a double acting cylinder on instroke, I need to watch the area, right? So let's look at the kind of question. What we would call this red area in here, we would call that the effective area. EFF, the effective area. And you'd call that white area in here the area of the cylinder rod. Yeah. And you'd call that, because we're starting to make a distinction, you just call that the area of the cylinder, right? So that's like the big full area. That's the big circle area, AC. And the small one is ACR. And the red donut shape is effective area, AEFF. So how does it work mathematically? How are they related to each other? So the effective area is equal to the cylinder area minus the cylinder rod area. Big one minus the wee one, right? So they could ask you a similar question, but they'd have to give you a little bit more information. So let's say they said if force is 342 newtons and the cylinder diameter, the symbol for diameter, the cylinder diameter is 25 millimeters and the cylinder rod diameter is 6 millimeters. What will the pressure be? Or what will the pressure need to be? Okay, these two pieces of information here, they let us work out the effective area. Sorry, on in stroke. Let's get rid of that wee question mark there, because that's the full question. Okay, so the two data points allow us to work out the effective area. So it's the same deal, except this time it's the effective area we need to work out. So we know that we've got pressure is the thing that we're looking for. We've got a force of 342 newtons, and we can work out this effective area because it's on in stroke. It says in stroke in the question, so we know that it's effective area that we need. So that's the cylinder minus the cylinder rod, area of the cylinder minus area of the cylinder rod. Okay, so let's work out AC first. So pi r squared equals, the diameter is 25, so that's 12.5 for r, 12.5 squared, and that's at 28.27. That might not be right, I might end up coming back to that. And then ACR is pi r squared, and that's 6, so that's pi multiplied by 3 squared equals. So 12.5 times 12.5, oh no, this is the 400 one, isn't it? Multiplied by 3.141, 491. That's not right, equals 491 millimeters squared, and then this is the 27 one, 3.141 times 9. Let's put the calculator on. 3.141 times 9. 28.27. So I can now work out my effective area given those two data points. So that's 491 minus 28.27 equals 491 minus 28.27, 46273. And that's me got my area. So now I can work out pressure. So pressure equals force over area, and it's going to be 342 divided by 462.73. 342 divided by 462.73, 0.7391. 7391 newtons per millimeter squared, and then we would need to round it to the correct number, so that's 3 significant figures, 2 significant figures, 1 significant figure, so we're rounding it to 1 significant figure, 0.7 newtons per millimeter squared. It's quite a high pressure, 7 times atmospheric pressure. So that's the process that you'd have to do if it was a double acting cylinder on in-stroke working out effective area. Okay. There are another set of questions, or that's the kind of That's the top end level for National 5 Pneumatics maths, where it's in-stroke double-acting cylinder, you need to work out effective area. There's other ways they could phrase the question where they give you the force and they give you the pressure and they give you the 6mm cylinder rod, and then they ask you to work out what the diameter is. In that case, you're working out area from pressure and force. I'll do an example of this, but you're working out the area, and that's the effective area that you've just calculated. They're giving you the 6mm, so you can work out the cylinder rod area, and then you can rearrange that equation to give you the area of the cylinder, the big area. And then you'd need to be able to then convert that area into the diameter. I'll show you how to do that, but that's pretty much beyond the scope of National 5 at this point. Give me 2 seconds. Right, so before I do that other example, so what we've got here is like, these are the questions I'm going to ask you to do. There's 3 of the kind of easy standard ones. These ones are where I'm just asking you to work out effective area and area, where I've given you the 2 different diameters and just work out the effective area for in-stroke and the cylinder area for out-stroke. Right? Down here, these are the ones, if I give you a circle with an area of something, can you work out a diameter? And then required diameter. These are the kind of more difficult questions. So let's stick in another quick example then. Yeah, I don't understand why sometimes this doesn't work. Oh, for goodness sake. Yeah, so what I'm going to do is give you an example where you've maybe to work out the diameter of the cylinder from this kind of stuff, right? Okay, so if the pressure is 0.30 newtons per millimetre squared and the force is 199 newtons and the diameter of the cylinder rod, the thin bit, is 9mm, what is the required diameter of cylinder? On in-stroke. So what we're going to do, I'll write out kind of bullet points what we're going to do first. We're going to use P and F to get the effective area. Yeah. And then we're going to use the diameter of the cylinder rod to get the area of the cylinder rod. And then we're going to use the area of the cylinder rod and the effective area to get the area of the cylinder. And then we're going to use the area of the cylinder to get the diameter of the cylinder. I think that's going to be the process. So let's do step 1, use that pressure and force. So area equals, so remember you'd start off with pressure equals force over area. And because it's in stroke, that means that that's the effective area. So if we rearrange this, area equals force over pressure, effective area. So the effective area equals 199 divided by 0.3. 9 divided by 0.3. 663.33, so on and so forth. So that's your effective area. Use the diameter to get an area. Okay, so the area of the cylinder rod is pi r squared. So half of that's 4.5, so that's pi times 4.5 squared. So the area of our cylinder rod equals, so 4.5 times 4.5 times 3.141. 63, oh that's nice, 63.61. 63.61 millimeters squared. Then we're going to use those two values to get AC. So do we know that the effective area equals the cylinder, the area of the cylinder minus the area of the cylinder rod? And we want this guy, so we're going to rearrange it for this guy. All we're doing is moving this guy over the other side, and it becomes plus. So that means that the area of the cylinder equals the effective area plus the area of the cylinder rod. Alright. And we can plug those two numbers in. So we've got our effective area, 663.333, plus the area of the cylinder rod, 663.61 equals, so 663, 726.94. 726.94 millimeters squared. So that gives us the area of the cylinder, but that's not what we're asked for. We're asked for the diameter, right? So if you know that area equals pi r squared, you could rearrange that for r. So you put the pi over the other side, so that would be 8 divided by pi equals r squared. Put the square over the other side, and it becomes the square root of a over pi equals the radius. It's not the radius we want, it's the diameter. So, diameter, a funny symbol again, equals 2 times that. Area over pi. Again, this is what kind of separates this question from Gold Standard National 5 to extension work. This rearranging this equation isn't something you're normally asked to do at National 5. Let's stick it in there and see. So 2 multiplied by the square root of 726.94 divided by pi equals. So we'll divide that by pi. Find the square root of that. And then multiply by 2. 30.43 equals 30.43 millimeters. Look back at our original data. That's 2 significant figures, 3 significant figures, 1 significant figure. So we need to round this to 1 significant figure, which equals, nicely, 30 millimeters. So if we had a 30 millimeter diameter cylinder with a 9mm cylinder rod, and we supplied it with 0.3 newtons per millimeter squared, it would generate a force of 199 newtons. Fantastic. That's it. That's the whole process. So you can see these questions here that I'm going to ask you to do. The first 3 are just find the missing one, calculate area, calculate pressure, calculate force. These ones are calculate the area and calculate the effective area. So I'm expecting 2 answers for question 4, 2 answers for question 5, and 2 answers for question 6. But I'm only expecting areas. I'm not expecting you to do pressure or force in these ones. Down here, calculate the diameter of a circle with an area. So I'm just going from area to circle just to kind of introduce that difficult bit. And then question 9 is essentially what question 9 and 10 are essentially what I just did in that example there. Okay. So that's you got 10 questions to do and a lot of knowledge behind it. Make sure you copy out those examples and ask me any questions if you need to before you attempt these questions. Thank you.